Okay, we're going to start here on Chapter 9, intersections of lines and planes, and then planes and planes eventually. But this is going to be on lines and planes and lines and lines. Okay, so first of all, we have, I've drawn some pictures here of the possibilities of intersection of a line and a plane. Okay, so the most common one, if you just randomly chose a line in 3 dimensions and a plane in 3 dimensions, you would end up with this picture right here. The line would probably intersect the plane at one point. Okay, and randomly selected lines and planes, you would probably rarely come up with this, and that would be a line that lies on the plane, so they're coincident. Okay, and the intersection of these, this line and the plane, if the line lies on the plane, would be the line itself. And then the other situation would be that the line is parallel to the plane. Okay, so the line's parallel to the plane, which means there is no intersection point. Okay, so then we have those three for a line and a plane. And then we have, for a line with a line, we can have this situation right here. So you've got the line and the line intersect in 3 dimensions. Now this is pretty rare. If you chose 2 lines randomly in 3 dimensions, it is very rare that they would actually intersect. Okay, so if you took 2 pens and just threw them up into space randomly, and then you said freeze, they would probably not be intersecting if you extended them infinitely. Okay. The second option here, if you chose two lines randomly, this is probably the most common case. They would be skew lines. They don't intersect and they're not parallel. Okay. And what's coming up in the future is we're going to look at the shortest distance between 2 skew lines, and this would be it, a line that's perpendicular to both of them. So this is supposed to be an image of 3-dimensional 2 lines. They're not parallel and they don't intersect. One sort of runs over the other, like 2 airplanes passing in the sky going different directions. Okay, and the third case is that the lines are parallel. Okay, so there's no intersection in these last 2 cases. All right, so let's take a look at the intersection of a line with a plane. So a line with a plane. Here is an example. Okay, so we've got the plane here, pi 2x minus 3y plus z minus 6 equals 0. And the line, this is the parametric equation of the line. It's the parametric equation of a line in 3 dimensions is going to be the easiest thing to work with. Okay, so this is a fairly straightforward case. What we want to do here is at an intersection point for a line and a plane, or a line and a line, we're looking at the points that are in common. So the intersection point, we know that the x-coordinate, the y-coordinate, and z-coordinate are all the same. So let's make an assumption here that there is an intersection point between this line and this plane. And if there is, well, I can substitute in the expression for x here into there, because the x is going to be the same at the intersection point. Same with the y, I sub that in there. And the z, I'm going to sub this in for z. Okay, and when I do that, okay, so sub the expressions for each one of those in for the variables in the plane, I then end up with an equation here that has just one variable, t. You can rearrange that. This is a grade 9 problem. Just rearranging this, isolating t, and you get t equal to 1/3 in this case, or negative 1/3. Once you have t, well, you can go back up to the line here and notice that if t is a specific value, you're going to get a point on that line. So we do have a specific value for t. We have t equal to negative 1/3. If we sub that in, we will get the point of intersection. Okay, so we sub t equal to negative 1/3 into the line, and we get the intersection point here. Just by evaluating, we get the point of intersection is 4/3, negative 2/3, and 4/3. You can check this. You can sub this into the equation of the plane for x, y, and z and check that it works. Okay? All right, another example on this. So you might want to take a look at this example, then pause the video and try it. See if you can get it, and then you'll see the rest of the solution after. Okay, so I'm giving you another one here where the plane is x minus y plus 3z minus 4 equals 0, and the line is this one right here. Okay, so now if you've tried it, let's see if you got it right. So sub L into pi, so sub the line into the plane, just right like we did before, subbing the expressions for the expression for x in for x, the y expression in for y, the z expression in for z, and then we evaluate and we get t equal to 5/4. Okay, so check your work on this. And then take 5/4 and sub it in for t in the equation of the line. Okay, so back here, the equation of the line, we have a specific value for t. We can sub it in. Okay, sub it in, and we get the values 7 for x, negative 15/4 for y, and negative 9/4 for z, and that's going to be our point of intersection. Again, you can check this by subbing in these values for x, y, and z in the equation of the plane to make sure that it equals 0. Okay. Now, what happens when you solve this in a situation where the line doesn't intersect with the plane? Well, if the line doesn't intersect with the plane, then the line must be parallel to the plane, and you wouldn't get a value for t. You'd probably get something that looks like 0t. 0t equals 7. Okay? That would mean the assumption that there is an intersection point is wrong. So we're assuming that there is an intersection point and that the x, y, and z values are the same for both the line and the plane. If we get to an untrue statement like 0t equals 7, then our assumption must have been wrong, and there is no intersection point. Okay, so if we can't solve for a value of t, there mustn't be an intersection point. And the other situation would be, what if you got something like, so the last situation was 0t equals 7. That's just not true, because that implies that 0 equals 7, and that's not true. So our intersection point doesn't exist. The line is parallel to the plane. If you had something like 0t equals 0, well, that's true for any value of t. So we don't have one specific value of t, we have every possible value of t. So if we go back up here and we sub in every real number in here for t, the intersection points are the line. So when the line is coincident with the plane, meaning lies on the plane, when you try to solve for the intersection, you're going to get something like 0t equals 0. A true statement where you can't get one specific value for t because every value works. Okay? We'll look at that again later. Okay, so this is the solution to this problem. All right, the next one. The last two were nice because we had the equation of the plane in Cartesian form. What if we don't? What if the equation of the plane is in vector form? Okay, so if it's in vector form, then you have a couple choices. Convert it to Cartesian by taking the cross product of these vectors to get the normal, and then plugging in the point to get d, and doing it the same way we did it. Or, if you're asked not to do that, then you want to convert the plane to parametric form. And remember, the x's, y's, and z's are all the same at the intersection point, so we're going to compare all those values. Okay, so from the line, here's the x, y, and z. From the plane, here's the x, y, and z. And when we work this all out, we've got 3 equations with 3 unknowns. Now this one's nice because we can get t right away. There's no k in the second one, and there's no s in the second one. So we can solve for t equals -6. Sub that into equation 1 and 2, and then you've got 2 equations with 2 unknowns. So sub it into equation 1, we get this equation. Sub it into equation 3 and evaluate, we get this equation. So now we have 1 and 3 with 2 unknowns instead of 3. Okay, so that's a way to eliminate that down. Otherwise, if there was an s and a k in this, then you'd have to use the first 2 to eliminate a variable, say t, and then the second 2 to eliminate the same variable t, and then you'd have 2 equations without the variable t in it, just k and s, and 2 equations with 2 unknowns you can solve. Okay, so in these ones, I'm going to sub 3 into 1, so I'm subbing this into 1, and I get to solve for a value of s. I could have used elimination too. I used substitution because it seemed easier. So by subbing it in there, I get a value for s, which is -11/9. At this point, I've got s and t. I can go back to the plane, sub those in, and get the intersection point. Okay? If you want to check or make sure that a k exists, well, then you can sub s and t into one of the equations to solve for k. And you get k equal to -71/9. And k exists. So that means there is an intersection point. It's most likely that k would exist. If you just solve for k first, that would be easiest, and you could just get the intersection point there right away. Okay? So that's those examples. Okay, so once we've got s and t, I plug them in here to the equation for the plane to get the point of intersection. When I plug them in, I get -142/9 for x, y equals -4 for y, and z equals 80/9 for z. And that's our point of intersection. Okay. And as I mentioned earlier, so here's some statements here. So if the line and the plane are parallel, then you will get a false statement when you solve for the parameters. Okay, so when you're trying to find the intersection point, you'll get a false statement like 4 equals 3 or 0t equals 7, which is most likely it, 0t equals 7. There's an example like this on page 490, so example 2. If the line and the plane are coincident, then you'll get a true statement when solving for the parameter. Okay, so when you're trying to find the intersection point, you'll get a true statement like 0t equals 0 or 4 equals 4, which is independent of the value t. So t can be anything, and this means you have the line itself is the intersection. There's an example like this on page 491. Okay, and the last